Hi, seventh grade. Today we are working on activity 3.2 in our Earth Science unit, what makes the weather change. And for our background intro today, we have two balloons that are being part of a much bigger hot air balloon festival that takes place in Driggs, Idaho, which is one of my favorite places. I used to work at a scout camp right up there, right at the base of the Grand Teton, and that's where I met my cute boyfriend. So when I had to find a picture of Balloon Festival, I found that one. All right. So today's agenda, bell work, and then this video lesson. Then you need to do activity 3.2 on Google Classroom. It is form again. Also, please remember that I need to correct the short answer questions. And so you will not get a great score yet because half of the points are not graded yet, so be patient with that. Please make sure to always turn in your assignments, even if they are late. Just send me a note in the notification section at the top of the classwork page. For daily work today, your bell work is due as well as your assignment is due, both by midnight. Your objective by the end of this lesson, you will have watched a demonstration to investigate what happens when a small air mass is heated and cooled, and apply the concept of how hot air rises to how a hot air balloon works. So all of this is actually part of convection. Okay, so quick review. Convection is a type of heat transfer in liquids and gases. For most of these lessons, we're going to be talking about it in gases. Energy and matter are moved by buoyancy forces from one place to another due to differences in density. Remember, buoyancy means to be able to float. And so if it has a higher buoyancy force than another, one will float over another. Air mass is a volume of air that has the same air pressure, humidity, and temperature, not ant. An air mass can be cold or warm. Okay, yesterday we also did some models, so I included some of them. Thought you guys did a great job. That's just a few of you. So nice job. I believe Ticonderoga was in there twice, so sorry about that. So now let's look at the next part. We've got a system. A system is a group of objects that are working together. We talked about this in chemistry, and we're going to add something to this. A closed system is a system that allows the transfer of energy, but the rest of the system does not change. So you're going to see some examples of this in our video today. And here is the video. And I will be stopping it a little bit to explain about the closed system. Hi, seventh grade. Today we are doing activity 3.2 in our weather unit, and our concept again is what happens when air is heated or cooled. Yesterday we talked about convection and how that affects the weather. Now we're going to talk about what happens on a smaller scale when I heat air. So for my experiment today, I have two bowls about the same size. One of them is half full of ice water. And I'm going to put some boiling water in this one, and it's steaming back here. And then I have an empty soda bottle and a balloon. Okay, so empty, nothing in there. A little bit of water from when I rinsed it out, but nothing too big. So I'm going to put the balloon over the top. Let's see if we can get the balloon to go in the work right. Okay, so we're going to put the balloon over top of the bottle, like so. Okay, and you can tell there's no air in there. Okay, and we're going to see what happens when I put just the bottle inside of the bowl of hot water. Okay, what do you think is going to happen? Okay, take a second, think about it. Do you think the balloon's going to go up? Do you think the balloon's going to get sucked down? Okay, so let's remember what we learned yesterday with hot air. Hot air rises because it spreads out, it gets thermal energy, the molecules spread farther out, and it becomes less dense. When it becomes less dense, it becomes more buoyant, or it will float type of thing. So that air is going to move up, that air mass. Now I have a very small air mass in my pop bottle. And I want to know, do you think that it's going to go up into the balloon when I put it in the hot water, or do you think it's going to pull it down? Okay, so it sounds like my water's done. So we're gonna pour this in here until it's about the same height as the ice water. So we can keep our variables consistent. All right. Okay, so I'm gonna stop it right now. So our system is the bowls of water, the bottle, and the balloon, and the air mass inside the bottle. That's our system, okay? It's all these things that are working together. Now, the closed system is the bottle, the balloon, and the air mass inside. It literally is a closed system. The balloon is closing the top so no air can get in or out of the bottle except for what's already there. So there's our closed system, and here is our full system. Okay? So make sure we're in frame. Okay, you ready? So I'm just gonna set it down in here. Check it out. Okay, so while this is finishing, it looks like it's just about done. Did I add any more air molecules into the bottle? No, I didn't. It was sealed by the balloon. Okay, so let's take it out. And it still stays pretty big. It's starting to deflate. Think it'll work again? Let's try it. A little bit more. Okay. All right, now let's put it straight into the cold water. Okay, so that cold air is becoming more dense. When it becomes more dense, it's less buoyant and it sinks. So that's why it's gone down so far. Okay, there's still some up in here, but not nearly as much as before. Okay, and if I left it here long enough, let's see. Okay. So it is definitely deflating even more. Okay, you can see it on the sides especially. Yeah, okay. So again, the same amount of air molecules are in the air mass inside my water, inside my pop bottle. Okay, the only thing I changed, wow, look at that, it's totally deflated. Okay, the only thing I changed was the temperature of the air molecules inside. Okay, so in the next part of the video, we're going to see what happens and how we can apply this concept to something that we see a lot of here in Las Vegas. See you guys in a minute. Okay, so the next part of the lesson is applying this exact concept into hot air balloons, okay? How does that work? Does it work the same way on a bigger scale? Let's find out. Okay, where did our other slide go? I'm having some problems with my Google Slides, so let me see if it's... Okay, we're gonna pause for a second. I don't know if I can pause. Hang on. We will go on an excursion. I don't want to refilm this. All right, now you can see all the stuff I've been watching.
One of the great challenges in this world is knowing enough about a subject to think you're right.
This episode is sponsored by Dropbox. If it sometimes feels like the whole world is pressing in on you, well, that's because it is. A 1 square meter column of air above your head stretching from here to the edge of Earth's atmosphere contains almost 10 tons of air. That's a lot to carry on your shoulders. But if it ever feels like too much, you know what's a great way to get away from it all? balloons. That's not what I meant, guys. Not like that. Like this. Balloons are magical. Birds and planes stay aloft by using power to keep air moving over their wings.
We built blimps and party balloons with lighter gases like helium, but balloons like those weigh thousands of pounds. And they're not filled with helium. They're filled with the very same air they're floating in, yet they still go up. Now that you mention it, why does the atmosphere itself stay up? That column of air above your head we talked about earlier, well, it's the same mass as a couple of elephants. But just like elephants, air molecules obey gravity, and I don't see any floating pachyderms around. Think about it. Air is mostly empty space. If I was an oxygen molecule, I'd have to travel the length of a football field on average before I ran into another one. But occasionally, they do collide. Air molecules will fall until the collision's bouncing them up. The pressure is balanced by the weight pushing down on them. Up high in the atmosphere, there's not much air on top of us and not much colliding going on, so the pressure's pretty low. But down a little lower, we have a big mass of air above squishing down, so things get more crowded and the pressure is higher. This sets up a gradient all the way down to Earth. The lower we go, the air's more crowded. It takes more collisions to balance out all that squishing. Even though it's mostly empty space, air can still hold up a plane. I can sit in a chair in the sky riding on almost nothing and not fall to the ground. That is crazy. You may have heard that the Wright brothers are responsible for humans taking flight, but that's wrong. 120 years before them, in 1783, the Montgolfier brothers had the brilliant and kind of dangerous idea to light a fire underneath a cloth balloon, and humankind took to the skies for the first time. Heat is what is keeping this balloon up. You probably heard your whole life that hot air rises, but have you ever really stopped to ask yourself why? I mean, you know what? We're going to need a smaller balloon to figure this one out. Ah, that's better. This is the ideal gas law, and it tells us pretty much everything we need to know about how gases behave. Pressure is basically the force over a given area on a surface. Whether a balloon inflates depends on the difference in pressure inside and out. As we heat up air in a balloon, the molecules gain kinetic energy and start colliding with more force on the inside surface. The pressure goes up. As the balloon expands, that force is spread across a larger surface area, which lowers the inner pressure until the pressure on both sides is the same, or until it pops. But this balloon isn't made out of rubber. It's pretty rigid. Once it fills up, it can't really get bigger. But it does have one thing that the rubber balloon doesn't: a hole in the bottom. You know what the mass of air in the balloon envelope is?
This is 105,000 cubic feet.
We can calculate that with a little bit
That's
of
the
math.
math. That's 105,000. I don't know.
Well, I calculated it. When we first filled up this balloon on the ground, it held about 3,700 kilograms of air. Add in the basket, the fuel, the people, and of course the balloon itself, and that's another 500 kilograms or so. A lot of mass to lift. But then we added some As we're adding heat to this balloon, those air molecules are moving around faster and faster with more energy, and they're pushing on the balloon harder and harder. But the volume has remained the same. It hasn't gotten any bigger or smaller. The pressure's pretty much the same too. The balloon's not collapsing or popping. So that only leaves us with one other option. There must be less air in that balloon than when we were down on the ground. Hot air has leaked out the bottom. We're still being pulled down by gravity, but the equal volume of cold air around us weighs more, and it's falling down underneath us. Balloons don't defy gravity, they float because of gravity. Eureka! This is the principle of buoyancy that Archimedes noticed when he saw his bathtub rise. It's the reason that ships float, because the weight they hold is less than the weight they displace, and the water falls down around them. We know that buoyancy is due to gravity because bubbles rise here on Earth, and they don't rise on the space station. You said that flying a balloon was like what?
Flying in a hot air balloon is the closest thing to being a cloud that I can think of. We're just floating with the wind, as gentle as can be.
Flying in a hot air balloon kind of reminds me that we have something in common with fish, that we live in a fluid. It's just that ours is made of air instead of water. It's kind of like floating on a bubble. That's something that can lift all our spirits. Stay curious.
All right. There is one thing I did want to correct with him. He said that there was less air in the balloon. That is not true. And he says that he goofed that up in the comments. There's the same amount of air in the balloon, although some of it did escape from the bottom because it's not a completely closed system like ours was, but it's close enough to have the same results. All right. So, questions. What are the parts of the closed system in our experiment? If you remember, it's just the balloon, the air mass inside the bottle, and the bottle itself, because that is the closed part. It keeps all of that together. The water is not part of the closed system. It's part of the system, but not the closed system. Did the mass of the bottle, balloon, and air change during the experiment? Okay, so stop and think about it. Did I add more air into the bottle or the balloon? I didn't. It was a closed system. So the mass didn't change. Okay, the mass is still the same. The volume of the air mass increased. Okay, it got bigger as it was heated because the molecules absorbed the thermal energy and moved farther and faster apart, okay, from each other. What part of the experiment showed that the hotter, less dense air expanded? Well, the part with the hot part. So what part demonstrated it is the better question. That would have been when the balloon expanded. Okay? No one put more air into it. The air itself expanded. Okay? What happens to the air molecules in the bottle when they are cooled? They slow down and they get closer together. Okay? All right. Oh, there he is. All right. Well, we don't want to talk to you again. Okay, so your assignment today, after you watch this, is you have activity 3.2 in earth science, and there are a lot of questions that are from everything you need to know is in this video, okay, including the last one. So I hope you have a great day and a great weekend, and I will see you guys on Monday. Bye-bye.